Welcome back to the lectures on quantum chemistry and molecular spectroscopy. This is the continuation of the assignment 1 solutions discussion, and we will now look at part B, a few more problems. And let me recall the problem set from the assignment that was there in the website. Okay. Now, problem 3, the question is to obtain the expectation value. A wave function for a particle in one dimensional box is given. It is slightly different from what you are used to, that it is a combination of two wave functions for the particle in a one dimensional box with coefficients C1 and C2, and you are asked to calculate the expectation value for the energy and momentum of this particle. Okay. Now, this is typically what is known as a linear superposition of the wave functions. So, let me go to a new page. Okay. So, you have a wave function psi 1, this is problem 3, which is root 2 by L C1 sin pi x by L plus C2 sin pi 2 pi x by L. Okay. C1 and C2 are arbitrary coefficients, but they have to be determined, the relation between them should be determined by making the wave function psi 1 star psi 1 dx between 0 to L for the particle in the box to unity. Then recall that the expectation value of any operator A, which is written as A within the expectation value within the angular brackets, is given by the integral psi star A psi d tau divided by the integral psi star psi d tau, which is usually 1 because we have normalized the wave function to unity. This is in the state psi. We are asked to calculate the expectation value for the energy and momentum for the state. Okay. So, the first thing we have to do is to ensure that the wave function has this property, namely it is normalized. Normalize the wave function. Okay. Now, you have to recall the properties of the particle in a one dimensional box. The wave function square is 2 by L integral 0 to L C1 star sin pi x by L plus C2 star sin 2 pi x by L. This is psi star, this is psi star multiplying psi C1 sin pi x by L plus C2 sin 2 pi x by L dx, and which if you write in an expanded form, it is 2 by L, and you have integral 0 to L. You have C1 star C1, okay, with the integrand sin squared pi x by L dx, that is the first term. And the only other term which is important for normalization is the term 0 to L C2 star C2 sin squared 2 pi x by L dx. We do not worry about the terms C1 star C2 integral sin pi x by L sin 2 pi x by L dx between 0 to L, because these are orthogonal wave functions, and therefore, this integral is 0, and so is its complex conjugate. Therefore, of the 4 terms that you have when you take the product, only 2 of them are there. Therefore, this term is not needed And so, I will simply get rid of this from here, and what is left over is the integral with C1 star C1, and the rest of it is 2 by L 0 to L sin square pi x by L. You know that the wave function is normalized, this function is normalized, therefore, this is 1 and the other is C2 star C2 times 1. So, what you have is absolute C1 square plus absolute C2 square, that is equal to psi star psi 1 star x psi 1 x dx between 0 to L. That is what we did. Therefore, the normalized wave function psi 1 of x is the normalization constant, which is the square, n square is this. Therefore, you have to divide by 1 by square, you have to multiply by 1 by square root of n, which means that the wave function is 1 by square root of C1 square plus C2 square times you have C1 sin pi x by L plus C2 sin 2 pi x by L. This is the normalization property that you need to have first. And then with this normalization constant, you can calculate the expectation value for the energy as nothing but the expectation value with the Hamiltonian operator between the wave functions in the state psi 1. In the state psi 1, it is given by psi 1 star x. The operator Hamiltonian is minus h bar square by 2 m d square by dx square for the particle with the mass m acting on psi 1 of x dx from 0 to L. Okay. Therefore, this is a calculation that you have to do, and you know, since it contains psi 1 star psi 1, the function this is squared. So, what you have is 1 by C1 square plus C2 square absolute values multiplied by the integrals, the integral 0 to L C1 sin pi x by L plus C2 sin 2 pi x by L. This is the wave function. Okay. All of this multiplied by the operator minus h bar square 2m by 2m d square by dx square acting on the same wave function, okay, the same wave function times dx. Okay. You know that the individual wave functions, the wave function sin pi x by L, okay, has an eigenvalue h square n square by 8 ml square, n is 1. The wave function 2, this one has an eigenvalue h square into n square, n is 2 here, therefore, it is 4 h square by 8 ml square. So, the operator h acting on these wave functions gives you the following, namely C1 times h square by 8 ml square times sin, that is also a 2 by L, which you have to include here. That is a normalization constant for the individual wave functions. So, the operator gives you C1 times h square by 8 ml square sin pi x by L plus 4 C2 h square by 8 ml square sin 2 pi x by L, and that is from this operator, the operator acting on the function, the linear combination that we have. Okay. So, it gives you an energy, the corresponding energy for the first wave function and the corresponding energy for the second wave function 4 h square, and it gives you sin pi x by L and sin 2 pi x by L, and the square root of 2 by L is already here in the integral. Therefore, the expectation value E is now only given by this term multiplying this term, and you know that the wave functions are orthogonal. So, only the term sin squared pi x by L and sin squared 2 pi x by L would contribute to the overall integral. The cross terms will not contribute, the other things are constants. Therefore, you can write the answer immediately as 1 by C1 square plus C2 square times C1 square. I hope I wrote the C1 square, yeah. So, C1 star, C2 star. So, you have 1 by the absolute value of C1 square into H square by 8 ml square plus the absolute value C2 square by H square by 8 ml square times 4. So, this is the energy that you need to calculate. This is the energy. This is the average value. So, what you see is that the wave function which has the component C1 multiplying root 2 by L sin pi x by L contributes to the overall average energy by the factor of its eigenvalue. The root 2 by L sin pi x has for the energy operator this eigenvalue H square by 8 ml square multiplied by the absolute square of the coefficient. The C1 is a linear combination coefficient. So, the absolute square of C1 contributes with this energy and the absolute square of C2 contributes with the corresponding energy for the wave function root 2 by L sin 2 pi x by L. In fact, there is a general result that if psi is given as sum over n C n phi n of x psi of x, and if the Hamiltonian has phi n's as the eigenfunctions with energy E n phi n of x, then the average value E can be calculated by first calculating the normalized wave function. The normalized to psi n will be 1 by the sum of the absolute combination absolute square of the combination coefficient times sum over n C n phi n of x. So, this is the normalized wave function, and for this normalized wave function the average energy is contributed by the corresponding weight factors C1 square times E1 plus C2 square times E2 plus C3 square times E3 plus etcetera all the way up to Cn square times En divided by sum over n the absolute square C sum over I would use the label I. Yeah, I guess I am using n here. So, let us use that Cn square absolute. Okay. So, this is a general result. The average value for a state which is a linear combination of the eigenstates of the Hamiltonian with the eigenvalues En and with the linear combination coefficient Cn is given by the contribution the absolute square of Cn times En, but summed over every such state. This is a general result. Okay. In a similar way, if you have to calculate to the P, now you can see that P in the state of psi is given by psi star. The operator for P is minus IH bar d by dx psi, all are functions of x dx, and in this case of course the particle in the box is 0 to L divided by the normalization property of the wave functions, namely psi star x psi of x dx. For a normalized wave function, of course, this is equal to 1. So, all that you have to do is to calculate the P by differentiating the wave function once with the derivative and then calculating the integral with the cross products. So, if you are doing this here, you would get again 1 by C1 square plus C2 square. I am just writing the final form and leave it to you to calculate. The integral will be 0 to L, and also there is a 2 by L here. The integral will be C1 star sin pi x by L plus C2 star sin 2 pi x by L. Okay. This is psi star, and then the operator minus IH bar d by dx on the wave function C1 sin pi x by L plus C2 sin 2 pi x by L, okay, dx. Okay. So, this is the action. The action of the momentum operator on the wave function is all of this, and once you have done this, multiply with the wave function and evaluate the integral. So, you know that this will give you pi by L times cos C1 cos pi x by L, and the other will give you plus 2 pi by L C2 cos 2 pi x by L. That would be the derivative, again multiplied by minus IH bar. So, this is the effect of the momentum operator on the wave functions. These are not eigenfunctions of the momentum operator, they give you something else, and therefore, then you have to calculate the momentum by evaluating the integrals sin pi x cos pi x dx, sin pi x cos 2 pi x dx, and likewise sin 2 pi x cos 2 pi x, and so on. And I think the answer should be 0. Okay. Verify that answer. So, in the next part I will continue the next problem.